pH plays a critical role in all living organisms. Precise control of pH is essential to ensure that critical chemical reactions can occur. For example, in the body, blood is maintained between pH 7.35 and 7.45, while the stomach is maintained between pH 4 and 5. After eating, the stomach releases acid to drop the pH between 1 and 2, which activates proteins that assist in the digestion of food. The body makes constant adjustments to maintain the ideal conditions for life. When growing cells outside the body, a bioreactor is used to simulate these conditions. pH is one of the critical parameters that is monitored to maximize the yield of product generated by the reactor. Since pH is so important, let's explore what it actually measures. pH is a measure of the activity of positively charged hydrogen ions in solution. A solution with a lot of hydrogen ions is said to be acidic, while a solution with very few hydrogen ions is said to be basic or alkaline. A solution in the middle is considered to be neutral. The hydrogen ion activity of a solution is defined by a logarithmic pH scale that expresses pH in numbers from 0 to 14. Everyday items have different pHs for varying reasons. Bleach is basic. Deionized water is a neutral pH, and the carbon dioxide in beer makes it acidic. There are many ways to measure pH, ranging from basic litmus paper and colored dyes that are used with swimming pools to more exotic ion-selective ISFET and optical sensors. However, for a bioreactor, a glass electrode is the most versatile and accurate. The glass electrode works like a very weak battery. When the probe is inserted into an acidic solution with a lot of positively charged hydrogen ions, the probe generates a positive voltage. When inserted into a neutral solution, it generates no voltage. And when inserted into a basic solution, it generates a negative voltage. The signals generated by these sensors are extremely small, so they must be read by a high-quality voltmeter. To understand why a voltage is generated by the pH sensor, it is critical to understand what voltage is. To understand electricity, comparisons are often made to water. Electricity flows through a wire very much like water flows in a river. In these terms, voltage would be a measure of the pressure of the electricity flowing in the wire. Take as an example the water that flows in the Colorado River. The flow of the river is constant on a given day, but the pressure generated by that flowing water is not enough to turn turbines used to generate electricity. To increase water pressure, Hoover Dam was constructed to hold the water behind the dam. As water builds up on the upstream side of the dam, the pressure increases relative to the water on the downstream side. If a hole were drilled in the bottom of the dam, the water from the high-energy side would flow to the low side until equilibrium was reached, where the same pressure exists on both sides. Water, just like electricity, always flows from high energy to low energy. If water collects on the downstream side of the dam, the water would flow backwards through the dam and turn the generators in the opposite direction until equilibrium was again reached on both sides. With a hole in the dam, there's no way to maintain the pressure difference between the upstream and downstream sides. Instead of a hole, let's install a pressure sensor to read the difference in pressure on either side of the dam without releasing the water. If the downstream water is held at a constant height, the pressure sensor can measure variations in the amount of water on the upstream side. In this case, the downstream is used as a constant, and the upstream is our sample measurement relative to that constant pressure. A pH sensor functions in the same way, but instead of water pressure, we are measuring the pressure of the hydrogen ions in a sample relative to a known solution of pH 7.0. In a pH sensor, the dam is replaced with a specially formulated pH-sensitive glass, known as the glass membrane. When this glass is wet, it forms a gel layer. The gel layer that is in contact with the constant solution is known as the inner gel layer, and the gel layer in contact with the sample is the outer gel layer. Hydrogen ions from the respective solutions can flow in and out of the gel layer, but other ions in the solution cannot. The result is a pH-specific difference in voltage on either side of the glass. When the concentration of the constant and sample is the same, the energy on either side is the same. A sample with a lot of hydrogen ions relative to the constant side results in a positive voltage. A sample with fewer hydrogen ions results in a negative voltage. Zoom out and we see that the special pH-sensitive glass is only found in the bulb of the sensor. The shaft of the sensor is made from standard non-conductive glass. To measure the voltage generated by the pH differential, a special metal wire is connected to a voltmeter, then inserted into the constant solution to create the measure electrode. To complete the circuit, a reference wire is inserted into the sample. The result is a very unstable measurement because the voltage generated by the reference wire is always changing due to changes in the sample. To overcome this problem, the reference wire is inserted into a second glass tube that is filled with a stable reference solution. To electrically connect the wires, a small diaphragm, known as a liquid junction, is installed into the glass tube. The diaphragm creates an electrical connection by allowing a small exchange of liquid between the sample and the reference. Some sensors are pre-pressurized. This means the reference is under pressure to ensure there is a flow of reference solution out into the sample. This minimizes the chance of contaminating the reference with sample. In the modern pH sensor, the glass measuring electrode fits inside the reference electrode, making the probe more practical for online measurement. When we take this probe and insert it into an acidic solution like pH 1, the hydrogen ion concentration in the sample is greater than the concentration inside the measure electrode. So, a positive voltage of 355 millivolts is generated. When the probe is inserted in a neutral pH 7 solution, the voltage generated by the reference and measure electrode is the same. So the meter reads a 0 millivolt difference. When the probe is inserted into a basic pH 14 solution, there are more hydrogen ions in the measure electrode than in the sample. So negative 414 millivolts is generated. The measured voltage is actually the sum of 6 unique voltages that are formed at the interface of all the individual components that make up the pH probe. These potentials include the outer gel layer, the glass membrane, the inner gel layer, the measure wire, the liquid junction, and the reference wire. With so many different potentials, it might seem that interpreting the pH reading would be difficult. However, only E1 is dependent on the pH of the sample. By holding the other potentials constant, the relationship between the millivolt reading and pH is linear. The design and construction of the sensor is critical to ensure the potential E2 through E6 do not drift during normal use. In an ideal world, a plot of the millivolt measurement to pH reading would look like this, where the graph goes from negative 414 millivolts to positive 414 millivolts at 25 degrees Celsius and crosses 0 precisely at pH 7.0. No sensor actually achieves this theoretical voltage. The reading is always a bit higher or lower. And for this reason, it is critical to calibrate the sensor against buffers of known pH. Ideally, at pH 7, the sensor will generate 0 millivolts. In reality, a viable sensor can produce between plus and minus 47 millivolts at pH 7. This is caused by the sensor's 0-point shift and asymmetry potential. The 0-point shift results from aging and normal manufacturing variability, where the E2 to E6 voltages do not completely balance to 0 millivolts. The asymmetry potential results from a difference in thickness of the inner and outer gel layer. The inner gel layer is protected inside the sensor and remains relatively constant for the life of the probe. The outer gel layer is exposed to the sample where it can dry out, become abraded, or be attacked by chemicals from the process. The resulting difference in thickness creates an unbalanced potential and a slight shift of the graph up or down. The second inaccuracy that calibration compensates for is a change in slope. Ideally, as we step 1 pH unit from pH 7, 59.16 millivolts is produced. So the further we are from pH 7, the stronger the battery. Since pH 1 is 6 pH units from pH 7, the ideal voltage is 6 times 59.16, or 355 millivolts. As the sensor ages, the battery gets weaker and no longer generates 59 millivolts per pH unit. A sensor is still considered usable until the voltage generated drops below 85% of the ideal voltage. To compensate for changes in slope and 0 point, a 2-point calibration is required. To accomplish this, the sensor is placed in validated calibration buffers like pH 4.00 and 9.21, and the actual voltages produced are read and plotted. We can see that, in this case, the actual voltage at pH 4 is higher than the ideal line. If we just use this 1 point and then assume the line crosses pH 7 at 0 millivolts, the predicted reading in a basic buffer will be well below the ideal line. However, when plotted, the actual value at pH 9 is above the ideal line. By using these two calibration points, a straight line can be plotted, and the equation for this line can be used to convert millivolt readings into pH. Over time, activities like autoclavation, CIP, SIP, and general use attack the gel layer, clog diaphragms, and contaminate the reference, causing some potentials within the sensor to change. And then a new calibration is required to maintain an accurate measurement. So far, we have assumed a constant temperature of 25 degrees Celsius for measuring pH. However, just as batteries do not generate as much voltage when they are cold as when they are hot, the same is true for pH measurement. As the temperature drops, the hydrogen ions become less active, meaning that at low temperatures, we will see less voltage generated per pH unit. Conversely, at higher temperatures, more voltage will be generated for every pH unit. Changes in temperature affect the slope of our plotted line. Higher temperatures result in a steeper line, and lower temperatures result in a flatter line. Most transmitters have the ability to compensate for changes in temperature using either an external temperature sensor or a temperature sensor that is built directly into the pH probe. To achieve the highest accuracy possible, calibrate the sensor at the same temperature as the sample. With all variables accounted for, a glass pH sensor can achieve an accuracy of plus or minus 0.05 pH units, with a precision of 0.01 pH units. This makes the glass sensor the most robust and reliable device available for the measurement of pH.